All right. Any questions about anything before we keep going on with stuff we've been talking about? All right. Well, let's do another example with finding an inverse using elementary row operations, and then talk about how we can write a matrix as a product of elementary matrices. So we've already talked about how elementary matrices give us row operations. So really all we need to do is keep track of the row operations. It'll tell us how to write the matrix as a product of elementary matrices. While that doesn't seem to have a lot of point right now, we will talk a little bit later about how we can use this idea to help us solve systems of equations, which is actually how typically computers will solve systems of equations. So we'll talk about that later on, probably next week. So anyway, let's look at another example, and hopefully the numbers won't be as gross as they were last time. So this is 7a on page 58. So the matrix we have is 3, 4, negative 1, 1, 0, 3, 2, 5, negative 4. And we want to find A inverse. So again, remember our MIG technique here is going to be augment the identity matrix. And put this matrix in reduced row echelon form. And if we see the identity matrix on the left-hand side of the vertical bar here, then the right-hand side has to be the inverse. Basically, we're thinking about solving a system of equations, if you will. We're going to multiply, really we're just solving a matrix equation. We're going to multiply both sides of that equation by an elementary matrix, by the same matrix, and do that over and over and over and over again. They're all going to be elementary matrices so that they perform the row operations, and we'll get the identity on this side, right? So then we'll have a bunch of elementary matrices multiplied together that tells us what A inverse has to be. That's the idea behind this. All right, so first we want to get a 1 in the upper left-hand corner. What's probably the easiest way to do that in this case? Swap row 2 with row 1, right? So do row 1 and swap it with row 2. And make sure that whatever you're doing with the quote-unquote left-hand matrix, you do with the right-hand matrix, right? Make sure you do it all the way across. It's easy to forget to do it. There's lots of little places here where you can make errors. I encourage you to use your calculators when you're doing these step by step. If you make a single small little arithmetic error on the exam, and it's like one error, but you do everything else right when doing this process, I'm not going to take off. Now you make multiple errors, I'll start taking off. But the point is making sure that you understand the process. And if you make one small little error somewhere in the middle, don't spend 20 minutes on an exam trying to find it. Okay? My point. All right. So the next thing we need to do is what? Okay, so how do we do that? Okay, and multiply the first row by -3 and add it to the second, and do the same thing except do multiply by -2 and add it to the third. Okay, cool. So again, that one's not going to change row 1. When we do that for row 2, well, hopefully we get a 0 there, because that was why we did that, right? And then 0 times the -3 is going to give me 0, so I get a 4. What do we get, -10 in the next line? And then the only thing that's going to change on the right-hand side there should be that -3 here, that second row. Do the same thing for the next one. We should get a 0 and a 5 And then -6 plus -4 gives me -10. And then I get 0, -2, 1. Now, I'm in a habit of writing down my row operations anyway, but for these problems, you definitely want to write down the row operations that you're doing if we're going to, at the end, write down a product of elementary matrices. Okay, otherwise, you have to go back and figure out what you did at each step to go back and get the elementary matrices. So in this case, it's very, very helpful to write down the steps so that you know how to go back and get those elementary matrices. Okay. All right, next thing we need to do is what? Okay, so turn that 4 into a 1. What do you want to do that? Okay, yeah, let's do 1/4 times that. Sure, that'll work. So I get 0, 1, -5 halves, 1/4, -3/4, 0. Like I said, sometimes you just can't avoid fractions. I will do my best on the exam to make problems that don't have as many fractions in them. You're not going to have like 70/4 like we did on Friday. That I can promise. So far, so good? Yeah. Oh, I don't know why I changed the next one. Yep, sorry. So no, it was not so far so good. Why did I change it? Because I was trying to talk at the same time and wasn't thinking about what I was doing. All right, next we want to do what? Good. Turn the 5 into a 0. Good. And to do that, we'll do what? I think I make that a 0. Good. So it doesn't change the first 2 rows here. Goodness. So 0, 0. What do we get? 25/2. And then it'll be -20/2. So we'll get 5/2 here. And get 0 here. 15/4 minus 8/4. So we should get 7/4 here. And then a 1 here.
Why would we get 0 in the first one?
Because I made an error. Thanks. Oh, it's a Monday. That's okay. Well, last class, whole screen just crashed. Lost my recording for the first half of class, so that was fun. No idea why I did that either. That's why I'm using a different program right now to record today, or at least for this class, because I have no idea what the heck even happened. All right, next step. Okay, so we'll multiply by 2/5. I'm glad everybody is paying attention though and correcting me as I go along. All right, so we get 0, 0, 1. Multiply by 2/5. So we get what? -1/2 here. And 2/5 times the next one's going to give me 7/10. And 2/5. It's really a 4. Why is it so shaky? The And now just a couple more to go, right? We need to do -3, row 3, added to row 1, replaced row 1, and 5/2, row 3, added to row 2, replaced row 2. So in row 1, we'll have 1, 0, 0. What? 3/2, -21/10, minus 10, plus 10/10 gives me -11/10. And then what? -6/5. Okay, good. 0, 1, 0. 5/2 times -1/2 is -5/4, plus 1/4 gives me -1. 5/2 times 7/10 gives me 7/4 minus 3/4, which gives me a 1. And then I get another 1 here. All right, so again, what this tells us is that the inverse of A that we started with is what's on the right-hand side of that vertical bar now. And again, we could check that it really is the inverse by multiplying it by the original matrix. We should see the identity. Besides, my arithmetic error is notwithstanding, the process okay for what we're doing. So again, just to illustrate what we've done, if we go back through the different operations, the matrix we started with was that 3, 4, 1, -1 business. Each of these now corresponds to an elementary matrix, right? So what this tells me is that, just to write this down, we started with our matrix A. Oops. And I'll just write it as A. The first thing that we multiply by on the left was that elementary matrix that swapped the two rows. Right? That was the first thing we did. Right? And the next thing we did was, actually the order doesn't matter much what we did here, but we did those two row operations. We did -3 times the first row and added to the second. And we did -2 times the first row and added it to the third. That was the next thing we did. Okay. It's going to be a long string. I'm going to shrink my screen a little bit. Now, I may move this over a little bit because apparently it's not letting me scroll. And then the next thing we did, go back up, we did 1/4 times row 2. So the elementary matrix that would correspond to that is that. And then we did -5 times row 2 and added to row 3. So that would be the elementary matrix that does that. And notice I'm writing this right to left because remember each time we're multiplying on the left. So it's building it up to the left as opposed to the right. Okay. And we got 3 more to write down here. We did 2/5 times row 3. to move this over a little bit more again because I'm going to run out of room. And then we did, and actually the order of the next two don't matter because they actually commute. We did -3 times row 3 added to row 1. We did 5 halves times row 3 added to row 2. After we did all of this mess, we got the identity. Right? So again, the reason why I'm doing this part right now is a couple of reasons. One, illustrating why what we did worked as far as getting the inverse. Okay? So again, this whole process was to put A into reduced row echelon form through row operations, right? Doing all of this mess was to put A into reduced row echelon form, right? Since we can do the row operations through matrix multiplication, and in particular through elementary matrices, the product of these things must be the inverse of A. We know inverses are unique, so when we simplify that whole thing that's inside, or not inside, but to the left of A, when you simplify that whole thing, you must get the inverse of A, because inverses are unique. We've already talked about that, right? So this thing has to represent the inverse of A. When we've got it in the augmented matrix, all we're doing is keeping track of that product. That's all this is doing. So that we know when we're at the end, we've got the inverse. Now, again, the idea of being able to do this with elementary matrices is going to have an application, like I said, next week most likely is when we'll talk about that. But for right now, it also allows us to write A as a product of elementary matrices. Because all I need to do is move this whole product to the other side by doing the inverses. Okay? So if a problem asks you to write A as a product of elementary matrices, you're going to do the inverse of each of these elementary matrices in the reverse order. Right? Because when you do the inverse of a product, it's the product of the inverses, but you have to reverse the order. Right? So the first thing will be the, for heaven's sake, the first thing will be the inverse of this thing that's on the right. Well, what's the inverse of a row swap? How do you undo the row swap? Just swap it again, right? So the first matrix will be 0, 1, 0, 1, 0, 0, 0, 0, 1. Let's go to the next one. How do you undo adding -3 to row 2, or -3 times row 1 and added to row 2? How do you undo that? To undo adding by -3, you're going to, okay, subtract -3 or just add 3, right? So the next one would be 1, 0, 0, 3, 1, 0, 0, 0, 1. Likewise, to undo adding -2, you're going to add 2, yep. Basically, all we're doing is just taking the inverse of each of these matrices and moving it to the other side. So it's getting, the order is getting reversed. The next one, we have to undo multiplying row 2 by a quarter. How do you undo multiplying by a quarter? Multiply by 4, good. Should write smaller. Here is, and this, the rest of these are just similar to it, right? In the next one, we added -5, so we will need to add 5. And then we, let's see if I can move this over a little bit. we need to multiply by 5/2 to undo the multiplication by 2/5. I'm going to write this on the next line because I'm tired of shrinking things. And then we need to add the 3 back. And we need to subtract or add the negative of 5/2. So we have A as a product of elementary matrices here. Any questions on how I found any of those, by the way? Remember again, the inverse of the elementary matrix is an elementary matrix itself. It just undoes the row operation that you did, right? So that's all how we're getting all of those. Like I said, you're probably thinking, why in the heck would I ever want to do that? And that's a good question. Why in the heck would you ever want to do that? Okay. Like I said, we're gonna talk about why we would care about a specific set of these things, not the whole thing. But being able to write something as a product of elementary matrices can help us solve systems of equations more efficiently using a computer. One of the reasons why you care. So we'll talk about how that process works. Like I said, later in the week. Or later in the week or next week. Probably next week before we get to it. Any questions on any of that at all? All right. Let's do another one. This is actually 7b. All right, so we've got -1, 3, -4, 2, 4, 1, -4, 2, 9. So same process, we're going to try to find an inverse for the matrix. First thing we need to do is what? Okay. Let's see if I can be a little bit more careful as we go along here. So we made that upper left-hand corner a 1. Next thing we need to do is what? Oh, jeez. Like I said, let's see if I can be a little more careful. No, I can't. Apparently, that's not possible today. And this is why I said that if you make a 1 arithmetic error as you're going through these things, I'm not going to count off. The process is the more important thing. Oh, goodness. Okay, what's next? Thank you, Shay.
-2 row 1 plus row 2, and then 4 row 1 plus row 3.
Okay. All right. See if I can do this one better. Maybe I should let somebody else do it. Maybe I should let somebody else just come up here today. 0, what do we get? 6 plus 4 is 10. -8 plus 1 is -7. And then I get 2, 1, 0 for the next one. Yeah. For the next one, we get 0. -12 plus 2 is -10. I missed a negative sign on this 4 too. Didn't I? Did I? No, I didn't. No, that's okay. Something's not right.
So we multiplied the top row by -1, so they're probably should be -6.
Because it started with a -4 here. I think we're okay. Oh, I know what I did wrong. I knew what the answer was supposed to be in this problem. I wrote the problem down wrong. There's a negative on this 9. I knew what the answer was supposed to be at the end for what I wanted, and I wasn't getting that. I knew there was a negative sign missing somewhere. 16 minus 9 gives you a 7. -401. Maybe that was like a 7. All right. Now, if we're putting this in reduced row echelon form, technically the next step would be to put a 1 here, right? But to illustrate what I want, look at this second row compared to the third row. If we add these two together, I'm going to get a row of zeros at the bottom, aren't I? For that particular matrix, right? So if we do that, if I just do row 2 plus row 3 and replace row 3, like, I really do prepare for class, I promise. Like, I know what this answer is supposed to be. 2, 1, 0, and you get 0, 0, 0, and then I'll get, it doesn't really matter what we get over here, -2, 1, 1 is what we'll get there. That side doesn't matter. The important part is this row of zeros here. So think about what we've done so far, especially in terms of elementary matrices. We've taken the matrix on the left-hand side, we've done some row operations or multiplied by some elementary matrices, and we've come up with something with a row of zeros. Am I ever going to see the identity on the left-hand side when I do that? No. I'm never, ever going to be able to get the identity on the left-hand side. Which means that I can never, ever find the inverse of this matrix. When I row reduce it, I'm going to always have a row of zeros. Okay? So never, ever am I going to be able to row reduce this and get the identity matrix. So what this tells us here at this point is that A is not invertible. Or again, remember another word for that is singular. Not invertible and singular mean the same thing. It doesn't have an inverse. So it's impossible to find an inverse for A here. So if you go through your row reduction and get to a row of zeros, you're not going to be able to find a row, find an inverse for that matrix. All right. Questions on that at all? So if you go through row reduction, end up with a row of zeros, you know to stop and say it's not invertible, and you go on to the next problem. Fine. All right. So one of the things, like I said, is going to be a theme in the course, besides solving system physics equations, is how can you tell if a matrix is invertible? So you might want to put this on a separate sheet of paper. Because we're going to add more conditions to this later. We're going to have like 20 of these things. So we'll want to refer back to it later. All right, so this actually starts off as theorem 1.5.3, but it'll continue on as we go along. But what we say is for an n by n matrix, the following n by n matrix A, the following statements are equivalent. If you've had discrete math and you've heard of if and only if statements, or just talked about if and only if statements in general in a math class, if and only if means that if one thing's true, the other has to be true, and vice versa, right? If and only if means it works both ways. So what the following are equivalent means is that we have a whole bunch of if and only if statements all piled together. That if you take any two statements and put if and only if in between them, it's a true statement. Okay, that's what this means. Okay. All right, so the first condition is A is invertible. second, I guess is letter A, is what the book uses. I'll use the same letter. B says that the system AX equals 0 has only the trivial solution. C says that the reduced row echelon form of A is the identity. I know, actually, they put the subscript in there too. And then D, A can be written as a product of elementary matrices. So what this means is that any of these conditions implies any of the other conditions. Like I said, if you take any two of the statements and plug if and only if in between them, it's a true statement. That's what it means for it to be equivalent. Now, if you're trying to, we're not going to go through the proof because I don't want to spend the time on it, but we'll talk a little bit about why they have to be true. But if you, typically the way you prove this in mathematics is to basically work in a circle. Assume A, prove B. Assume B, prove C. Assume C, prove D, and then assume D and prove A. So you get a nice circle. It's not the only way to do it, but that's typically how you do these kinds of the following or equivalent proofs. All right, well, think about why this has to be true. We will do A implies B here real quick because that's not bad. And we'll talk about the other ones. In order to do A implies B, if we suppose that A is invertible, how would we solve this matrix equation? What would we do to both sides? How do you get x by itself? So, yeah, usually if I think about it from an algebraic standpoint, we usually divide by A, but we don't divide by matrices. Instead of dividing by A, you would what? Multiply by the inverse of A, right? Multiply both those sides by the inverse, right? And the reason why we can do that is because why? What are we supposing in this case? Because you can multiply by, yeah, A actually has an inverse, right? That's exactly right. So if I multiply by both sides by A inverse, I get this. On the left-hand side, if I want to be really rigorous about it, I would regroup first, right? Right? On the right-hand side, when I take A inverse times the 0 vector, what am I going to get? The 0 vector, yep. Because again, remember when we write it in this form, we usually have a column of zeros. So if we take any row of A inverse and match it with the column of zeros, I'm always going to get 0 when I do that product, right? And then what's A inverse times A on the left-hand side? It's the identity matrix, right? So we get down to x equal to 0, and this is the only solution, and we refer to this as the trivial solution because it's the 0 solution. Okay. So the conclusion would be this is the only solution. All right. So anytime we have a system of equations where you have a system of linear equations where you've got the 0 on the right-hand side, or this matrix equation where we've got the 0 on the right-hand side, we refer to that as a homogeneous system of equations. I know some people pronounce it homogeneous, but math people pronounce it as homogeneous. So this refers to a homogeneous system of equations. When it's equal, and it's the equal to 0 piece here that makes it the homogeneous part. Important thing about homogeneous systems is they're always consistent. There's always a solution because there's always the 0 solution. I can always put in all zeros for all the variables and it gives you a solution. Typically, what you're interested in with homogeneous systems are the non-trivial solutions. When does it have non-trivial solutions? This pops up in particular in differential equations. A lot of differential equation stuff is based completely on that. Okay? So homogeneous systems play a big role in that. We'll talk a little bit about that later in the semester. So again, when you have the 0 solution, that's referred to as the trivial solution. So if the matrix is invertible, the associated linear system has only the trivial solution, which means it's not very interesting for our purposes. Is why they call it trivial. But all right, to go through the other ones, if you think about the associate, say if you wanted B implies C, for example, if this only has this trivial solution, that means when you row reduce it, you'd have to have x1 equals 0, x2 equals 0, x3 equals 0, right? Which means that you'd have to have 1s down the diagonal and 0s everywhere else, which means that has to be the reduced row echelon form. Right? Because think about what the final answer has to be. It has to be 1x1 equals 0, 1x2 equals 0, 1x3 equals 0. So you have to have 1s down the diagonal. For C implies D, we just did that, right? When we went through that specific example, right? If you multiply by the elementary matrices to get it to row reduce down to the identity, and then we can write A as a product of elementary matrices in that case. We just did that, right? And it's certainly a product of invertible matrices is invertible. So if it's a product of elementary matrices, then it's automatically invertible. So that's how that cycle would go. They go through that in more detail in the book. They actually go through the steps, but I wanted to go through one in particular and then talk about what you would have to do to prove that. Any questions on any of that at all before we go on to the next section? All right, so the first part of the next section, talks a little bit about more results with systems of equations and invertibility, much like what we just did for our proof here. So the long title to this section. Further results on systems of linear equations. Oops, systems of equations, it just says. And invertibility. All right, so in particular, one of the things they talk about in this section is basically a similar result to what we just mentioned with the trivial solution. So just to start off with this theorem, it says that if A is invertible, if I can spell invertible correctly, then for any n by 1 matrix B, which will denote like a vector B, the equation AX equals B has exactly one solution. A long statement for a theorem that we just basically proved in the previous, like 2 minutes ago. Go back up to this proof, or the previous proof that we did. I'll scroll down back in a second. If I go back to this previous proof, if I replace this with a B, then this gets replaced with a B, right? I would just rewrite the same statement here. Wouldn't I get the similar result? I would just have A inverse B on the right-hand side. Right? If I know that A inverse B, if I know A inverse exists, I can undo this multiplication and get X by itself. That's the whole point, right? If I get X by itself, then I have exactly one solution. It has to be the A inverse times the B. It's not any different than if you had 3x equals 12. You can undo multiplication by 3, right? And get X equals 4. Specifically, 1/3 times 12, right? The inverse of 3 times the 12. However, if you start with the equation 0x equals 0, I don't get a unique solution anymore. I can't undo multiplication by 0, right? So if it's not invertible, if we have a non-invertible matrix, I don't necessarily get a unique solution. Okay? I do if it's invertible. I'm guaranteed that I do. But if it's not invertible, we might have some other scenarios that pop up. And those other scenarios, though, are what you would expect. So the other scenarios are every system of equations, it should be a linear system, has no solution, one solution, I should say exactly one solution, or infinitely many solutions. Again, the visual that you want to think of with this proof is lines. How can lines intersect? Well, they may not, right? They hit in one point, or you get the same line, right? The only possibility is you can't have a line bend and hit in 2 places, or 3 places. So for linear systems, you get none, one, or infinitely many. The way we prove this is we suppose we have 2 and show that we can actually generate infinitely many. So let's suppose that x1 and x2 are solutions to ax equals b. Let's I'll call it z equal x1 minus x2. If I do a times z, what do I get? What did we just say that z was equal to? x1 minus x2. What can I do with the a relative to the subtraction? Good. You can distribute it. Good. Now remember what we're supposing here. We're supposing that x1 and x2 are both solutions, right? Right? What does it mean to be a solution to an equation? If I plug in x1 into this equation, what am I supposed to get out then? B. And if I plug x2 into the equation, what am I supposed to get out? B as well, right? So this should turn out to be AB minus AB. What's that going to equal? 0. Good. So I get the 0 vector here. Does that mean that z is a solution to this original equation, by the way? No, because I don't have 0 on the right-hand side necessarily, right? Remember, what we're trying to do here is that if we have 2 solutions, I want to generate infinitely many solutions, right? Well, it's this piece right here that we're going to use to generate infinitely many solutions. In particular, if I multiply this z by any constant, will it change the right-hand side? No, because I can just pop the constant out in front and get the exact same computation, right? So that's exactly how we generate the rest. So now, if we do A times, we'll do X plus any constant, we'll call it T, times Z. T is a constant, so we can rewrite this as AX plus T times AZ. I remember we can pull that constant wherever we would like. The reason for that, again, is because when we do constant multiples of matrices, we end up multiplying the entire matrix by that constant, right? So it doesn't matter when we do it. We're going to multiply all the entries by it. Right. What did we just say that A times Z was equal to? For that specific Z, what's that A times Z equal to? 0, right? So we get, this is T times 0. What's AX equal? Shoot, sorry, I don't want AX, I want X1. What's AX1 equal to? We assume that X1 was a solution, so what's AX1 equal to? It's the B, isn't it? And so we end up with B. All right, so what does this tell us? This tells us that if x1 and x2 are different from each other, if I actually get two different solutions, then I can generate infinitely many solutions from this piece here. And it also tells us how we get the form of these solutions. We find one solution to the original system, and then all of the solutions to the homogeneous system. And this gives us a general solution to the problem. To talk a little bit about why we care about such things, one of the things that you do in differential equations is solve things like, you've all had calculus, so say you wanted to solve something like y prime plus 3y equals e to the x, say. Making it up as I go along here. If you wanted to solve this equation in general, you would first solve the associated homogeneous system, which would be this one. You can check that any constant times e to the negative 3x works for that. And then to find a particular solution that works, what would you need to do here to get, what is it? You need e to the negative, e to the 4x, does that work? See if I remember what. If I do e to the 3x, 4x.
Y prime plus 3y minus e to the x equals 0.
I'm doing, I'm trying to remember what I need to, I'm just thinking about what I need to multiply this by to get to the right answer, but it's not working. I'm just ignoring the e to the x part. The homogeneous part is the get rid of this part. So we would need to do, let me just do this real quick, e to the integral of 3x. So it would have e to the 4x, and antiderivative is 1/4. 3's don't cancel. Oh yeah, that's right, that doesn't cancel. Yeah, you can check that, sorry, that e to the, 1/4 e to the 4x, this y, solves the original. You can check that that works. I don't know why I was having a hard time with that. Sorry. So then your general solution, I just wanted to give you an example of where this comes in. I'm not going to expect you to do this. This is a differential equations question, but that's the whole point of why this works. Your general solution looks like this particular solution. One solution to the original plus all solutions to the homogeneous. That's the format of the solutions. You've got one solution to the original, which is a 1/4 e to the 4x, which you can check works. That really does give me e to the, whoops, it doesn't give me e to the x. Well, anyway. I'll fix it later.
Sounds good.
I know how to fix it. I'm being an idiot. Here we go. Just erase that 4. It's 1/4 e to the x works. All right, so this particular solution plus the general solution gives you all of them. That's the idea. But that's what the proof does. And it turns out that there's a lot of linear algebra in differential equations. I apologize for that. I should have been a little bit more careful with the example that was